There's a famous poem by William Blake, and it starts by saying, "To see a world in a grain of sand, and heaven in a wild flower." Well, we're going to go one better than William Blake today, because the world is just a finite structure. We're going to see infinite structures, entire categories of graphs and dynamical systems in single points. In other words, we're going to identify where these things live in the category of categories. So networks and dynamical systems are extremely useful, extremely important things in the world. And I think most people would agree that learning the definitions of such things is extremely important. But what we're going to do today is to find out how we can define these things categorically. And I think this is really quite a profound thing. So the way in which we're going to represent these things is so minimalistic. The way we define the category of graphs is just like this. So this tiny little expression here, if we know what it means, everything's there, and it represents not only all graph structures, but all the different ways we can compare graph structures, all the arrows between these objects, which are graphs. And similarly, the category of dynamical systems can be written like this. And so today, I'm going to talk about how these definitions arise and how we can identify these grains of sand, these objects, these tiny little dots in the category of categories, which represent these profound structures. Okay, so one of the best things about category theory is that we can use it to get a kind of large-scale view of mathematics. So if there are some mathematical objects we're interested in, let's say sets or maybe directed networks, we can ask ourselves, well, do these objects naturally live in a category? And very often they do. So one of the core examples is this category set, which has objects as sets, and the arrows represent functions. And so this is something that's going on in set theory, where we have these three sets and there's some functions between them. And we'd represent this in category theory, in this category of sets, like this. So these sets here are now represented by objects, and these functions are now represented by arrows. Well, that's all well and good, but what about if we're interested in more kind of structured objects? How about directed networks? They're very interesting and important. Can we form a category of directed networks? Well, we can, and I'm going to explain about that. But the real thing I want to get across in this video is that there's an extremely beautiful way of doing this. You see, when you make these kind of objects, you often have to sort of really scratch your head and think, well, what would be a suitable type of arrow that I could introduce between my objects? I mean, you want something that preserves the structure of your objects in some sense. The arrows that you pick, of course, they have to play the game of category theory. They have to have associative composition. They have to have identity arrows and so forth. So it can be quite challenging sometimes to come up with the proper notion of what the arrows might be between the objects that you're interested in. How are you going to compare them? So what I want to do today is to show you that there are cases, many cases, where all of these ideas come about so naturally. So we're going to focus on a couple of examples in particular. One is going to be a category of graphs, and another one is going to be a kind of category of dynamical systems, okay, very simple dynamical systems. So a dynamical system is just something where things move over time, okay? And we're going to find that there's an extremely elegant way to define what these categories are and define what the objects are and what the arrows between the objects are. And it just comes straight out of sort of notions from category theory. So there's really no work. And when we look at things from this viewpoint, I think it's quite profound, to be honest. I mean, to me, after I learnt about this, I feel like I don't look at mathematical objects the same way anymore. Because when you're looking at a particular kind of mathematical structure, often, you look at the definitions and it's a pair of this set with a mapping and such that these equalities have to hold. And it's every time you look at a new kind of mathematical structure, you've got to memorize this new definition. And it might have some similarities to some other mathematical structures, but it's not really clear, working at that kind of level, how all these structures are related to each other. But hopefully what I'm going to show you today is going to make you see things from a sort of higher viewpoint. Okay, so I want to start by talking about directed graphs or directed networks. And there's many different kinds of directed networks depending on what kind of restrictions you put upon things. For example, do you allow self loops? Do you allow there to be more than one edge connecting one vertex to another, sort of parallel directed edges? And let's say yes. Let's say yes to everything, okay? So we're really talking about what mathematicians call directed multigraphs with loops. Multigraphs because there can be multiple edges going in a direction between two vertices, and with loops, of course, because we allow a vertex to be linked to themselves. Okay, so we're interested in all directed multigraphs with loops. Now I'm just going to call those graphs from now on because it's easier to say, okay? So we have all these different graphs. So what are they? How do we define them? And more importantly, perhaps, how are they related together? How can we think of these things as living in a category? How can we make a category where every object represents one of these graphs? Okay, well, let's start with the first one. How do we define such a thing? Well, clearly such a graph has a set of vertices, basically these white dots here, and it also has a set of directed edges. But obviously these two sets are related somehow, and that's really what makes this kind of network structure. So how might that work? Well, let's think about this edge here, and let's call it E. And let's also label our vertices. So there's 1, vertex 2, 3, 4, and 5, okay? So we've labelled our vertices and we're talking about this edge. So how might we specify what this edge is doing? Well, it's going from vertex 1 to vertex 2, okay? So how can we specify that? Well, we could say that the source of this edge is vertex 1. So let's write that down. Let's write S for source. So the source of this vertex E equals 1. So we can imagine that there's this function here called source, and this is a function which is sending edges to vertices. In particular, it's telling us for a particular edge where the source of that edge is, where's the vertex that edge exudes from. Okay, so the source of this edge here is 1. So that's part of the information. What other information do we need? Well, we also need to know where these edges are going. So we could say that the target of this edge is 2. So we'll have another function called target. And this function sends an edge to where it's pointing towards. So this is our definition then of what a graph is. More precisely, what a directed multigraph with loops is. It's a set of vertices, a set of edges, a function S sending edges to vertices, and a function T sending edges to vertices. Does this allow us to express these kind of structures? Well, yes, we can have multiple edges which S and T act similarly on, and those would be considered kind of parallel edges. And of course, we're allowed to send the source and the target of an edge to the same vertex. That would define a self-loop for us. Okay, so now we know how to define a particular graph. But there are lots of graphs, and presumably they live in a category. So how can we think about what the arrows in that category might be? So we can scratch our heads and think, well, we have some sets here, they have some structure. Maybe we can think of some kind of a function which maps these sets to other sets and preserves the structure. But you know, that's there's a lot of different things that do that. It's quite a hard job then maybe to locate what's the proper notion of arrows between these graphs. Turns out that there's a much easier way. So let me just write something down which basically is going to tell us everything about this kind of category of graphs. And it's such a small expression, it's quite surprising. Okay, so this here, this tiny little expression actually tells us everything that we need to know. Okay, so I find this quite remarkable. And so once we understand what this means, it's going to tell us about all the objects in this category, all these graphs, and all the kind of notions of arrows between them. So I guess my next goal is to explain what this means. So what's going on here? Well, there are two different kind of pieces to this. There's this here I've written capital S-E-T, and here I've got this funny little picture at the top right. So what's this? Well, capital S-E-T, this is the category of sets, okay? So this is the thing I was talking about a moment ago. It's this category that has objects representing sets and arrows representing functions between sets. This is one of the most important structures in category theory, and we're very familiar with it. What about this funny symbol here? What does this mean? Well, this is nothing more than a picture of a category. So let me just draw this picture a bit bigger. What's this symbol here? Well, it's just a little picture of this category here. So this is a category which has two objects, which we call 0 and 1. And it has these two parallel arrows that we call A and B. Now, we also have these identity arrows, the identity arrow of 0 and the identity arrow of 1. But I haven't bothered drawing the identity arrows down here. So you might be feeling a bit confused at this point. What on earth does this category have to do with graphs? I mean, let's keep things separate here. These are graphs and this is a category. These are different things, okay? This, we can compose the arrows within. In a graph, there's no natural notion of arrow composition. So how could this possibly inform us that we're talking about a category of graphs? Okay, so just to give you a little preview, how can I express this information here? Well, maybe I could express it like this. So this information that I've written up here, defining what a graph is, if we want to express this in the category of sets, well, we have these sets here, the edge set and the vertex set, and we have these arrows here. These are representing functions. So a category theorist might well think of a graph as something which has a structure like this, okay? We have an edge set and a vertex set, and these two arrows, these two functions, the source arrow and the target arrow. which are defining where edges start and where they end. Okay, so hopefully this looks similar to this to you. So that gives you a bit of a clue maybe why this particular structure is appearing in our definition of this category of graphs. Okay then, so we can forget about that stuff temporarily. Let's just carry on thinking about what this expression means. Okay, so we know that this here is the category of sets, and we know that this thing here is just a little picture of this category here. We understand this category of two objects, and we understand this category set. Now, the final thing we need to do is know what this notation means. So what's it mean to put one category above another? Well, let's look at a more general example. How about a D with a C upstairs like this? What does this mean? So what this means, we've come across this notation before, it means the category of functors from C to D. Okay, so here's this category C, and here's this category D. And we may have functors going from C to D. So there's one, there's a functor F, there's another one G, and there's another one H. Okay, and so this category here, this category of functors, it has as objects these functors. Okay, so a object in this category is a functor from C to D. So okay, let's start drawing this category here. So the way it really looks as a category, of course, is that each of these functors is going to be a object. So there's going to be F, and there's going to be G, and here's H. So okay, we know what the objects are in this category. What about the arrows? Well, the arrows are just going to be natural transformations. Okay, so a natural transformation from F to G, let's say alpha, that's just going to correspond to an arrow in this category. Okay, so in the actual category, it'll just look like this. Similarly, we may have a natural transformation from this functor G to H. Say beta, and that will look like another arrow. Okay, so what's the final thing we need to know about this category of functors here? Well, we know its arrows are natural transformations. How do we compose those arrows? So this is just what they call vertical composition of natural transformations. So I'm going to go over a recap of this in a moment, but basically the point is there is a way of composing these arrows, a very simple way, and it leads to another arrow which we could call beta dot alpha. So this is really the kind of picture of what this category of functors, this functor category, looks like. Okay, it has objects as functors and arrows as natural transformations. And so what is this? What is this thing which I claim represents all graphs? Well, it's the category of functors from this two object category here to the category set. So that's the kind of big idea that I want to get across today. Okay, so let's just go for a really fast recap of how functors and natural transformations work. So say we have this structure in a category C and we do a functor on it. So we're going to send every one of these objects to an object in this category D. So we'll send object A to object F of A in D. And the arrows, for example, an arrow F in category C, gets sent to an arrow F of F. Okay? A functor also has to send identity arrows to identity arrows. So the final thing a functor has to do is preserve arrow composition. So if we had another arrow G coming out of here like this, then there'd be an arrow we get from composing F and G, something like this. We call that G after F. And that would have to get lifted by this functor G to become F of G after F over here. And we'd want that to be the composition of F of G and F of F. So that's a functor in a nutshell. Okay, so what about natural transformations then? Well, suppose we have another functor G, which is sending this structure here to some other piece of category D. Well, what's a natural transformation from F to G look like? Well, we could draw this as an arrow between functors, alpha, but what does it look like actually in the category D? Well, it's a family of arrows. So this natural transformation has different components. It has a component for every object in the category C. And the component associated with A will be an arrow from F of A to G of A. So we can call this alpha of A. And the Bth component will go from F of B to G of B. So there's alpha of B. And there'll be one arrow like that for every object of category C. And these natural transformations have to make squares like this commute, okay? So we can draw a little curvy loop like this to represent that this square has to commute. So that means that alpha B after F of F equals G of F after alpha A. Okay, so going along this path and composing gives the same thing as composing along here. So, okay, what about composing these natural transformations together? Well, suppose we have another functor, H here, which sends C into this part of the structure down here. And then there might be another natural transformation, beta, from G to H. So it has these components. So how can we compose these two natural transformations, beta and alpha? Well, all we do is just compose the components of these natural transformations. So we have the simple formula that for vertical composition, which tells us that the eighth component of this composition of natural transformations is just the eighth component of beta after the eighth component of alpha. So we simply compose these components to get the component of the composition of the natural transformations. Okay, so now we understand what this functor category is. We understand what it looks like as a category. And we know that this is just another functor category. And we know what the category set is, and we know what this two-object category is. So all we have to do now is think more clearly about what the objects and the arrows in this category represent. And we're going to see that the objects of this category are going to be graphs, and the arrows of the category are going to be what's called graph homomorphisms, things which preserve the structure of these graphs. Okay, so let's get on with our main task then, which is understanding what this thing means. So this is a category, and the objects are going to be functors from this category here to the category set. So here's an example, a functor I'm calling G. So what's this actually going to look like? So here's one of our two objects in this left category. It's going to get sent to an object in the category set. In other words, this functor is going to send it to a set. We could call that set G of 0. Let's call that set E. Okay. This other object here gets sent to another set. Let's call it V. So also under this functor, this arrow A from 0 to 1 gets sent to this arrow, S, from E to V. And similarly, B gets sent to an arrow T from E to V. So all we have to do now is just think, well, this is in the category set. So E is a set, V is a set, S is a function, which is sending E to V, and T is a function, which is sending E to V. Okay, we have these identity arrows. These identity arrows here just get sent to the identity functions of these sets, so we can kind of forget about them. The important thing is that this functor really gives us exactly what we want. An edge set E, and a vertex set V, and a kind of source function which associates every directed edge with a source, and a target function which associates every directed edge with a target vertex. So as I illustrated before, this information exactly defines one of our graphs, one of our directed multigraphs, possibly with self-loops. So there we are. We can see that functors from this category to set are really representing graphs. They have all that information in them. So all we have to do now is think about what the arrows are in this category. And remember, the arrows in this category are going to be natural transformations from one functor like this to another functor like this. So it turns out that those kind of natural transformations sort of naturally correspond to these kind of graph homomorphisms, these natural notions of what we can consider to be arrows between graphs in this category of graphs. Okay, so now we want to understand what the arrows are in this category. And they're going to be natural transformations. So we have a functor G embedding this category somewhere in the category set. That represents one graph. And we'll have another functor G bar embedding this category, say, somewhere else in the category of set. And that represents another graph. So an arrow then between this graph G and this graph G bar is going to be a natural transformation from this functor G to this functor G bar. So let's consider a natural transformation alpha. So what's it going to be? Well, for each object in the source category, there's going to be an arrow from where that object lands under G to where that object lands under G bar. So this will be the 0th component of this natural transformation. The 1th component will go from V to V bar. And the critical thing here is that the corresponding kind of squares have to commute. So this arrow here, A, gets lifted to an arrow up here and also an arrow down here, and that forms a square, and that has to commute. And similarly with the B. And so thinking about these commuting squares, we get two equations. So thinking about the S's, we know that going along S and then alpha 1 is the same as going along alpha 0 and then S bar. So what do these naturality conditions mean? Well, they basically mean that these equations hold. Okay, so in other words, going along S and then alpha 1 gives us the same thing as going along alpha 0 and then S bar. So that's this. Or similarly, going along T and then alpha 1 gives us the same thing as going along alpha 0 and then T bar. So that's this equation. So all we need to do now is interpret what these equations mean for our graphs. And we'll see that they really boil down to a very kind of natural notion of arrows between graphs. So firstly, what's alpha 0 here? Well, it's an arrow which goes from E to E bar. And it's an arrow in the category of sets. So what is it? It's a function. It's a function which sends the edges of this graph G to the edges of this graph G bar. And similarly, alpha 1 is a function which sends the vertices of graph G to the vertices of graph G bar. So that kind of makes sense, right? I mean, if you're going to do a kind of graph transformation, you want to send the vertices of your graph to the vertices of some other graph, the edges of your graph to the edges of some other graph. And it seems somehow that kind of graph transformation is being encoded by these natural transformations. But we know that they have to satisfy these equations. So what do these equations mean? Well, these are basically saying that two functions are equal, and this is saying that two functions are equal. So how can we understand that? So to understand what these equations mean, let's just consider how these functions operate on a kind of generic element of the input. So for any member E of this set E, this set big E, so in other words, for any edge of this graph G, we can just put this little e in here. And now if we think about what this means a bit, we'll see that it's a very kind of natural idea. So let's think about this function first. So we have this element E of our edge set. So what does that look like actually in a graph, in this graph G? So this element E, what it actually looks like in this graph, if we actually look at the graph, it would look something like this, okay? It's an edge E going from a source vertex SE to a target vertex TE, okay? So we understand what this bit means. Now, what about if we do alpha 1 on that? Well, that's essentially applying this kind of transformation alpha 1, which is going to map this vertex here to some vertex of our graph G bar. So here's our graph G bar, and this whole thing here is going to look like this. It's going to be alpha 1 of S of E. So that's going to be a vertex of this graph G bar. So okay, now let's try and interpret this part of the equation. What's this mean? Well, firstly, this thing here, what's alpha 0 of E? Well, that's just where E gets sent to under this kind of transformation of edges. So there's going to be alpha 0 of E. And then what's going to be S bar of alpha 0 of E? Well, that's just going to be the source of this edge here in this graph G bar. And we're saying that that has to equal this thing here. And that makes total sense, right? So all this boils down to is saying that we want the image of the source of our edge to be the source of the image of our edge. And this equation here has a very similar kind of interpretation. All it's basically saying is that we want the image of the target of our edge to be the target of the image of our edge. So all this stuff is basically telling us is that when we have an edge from one vertex to another, our mapping of vertices and our mapping of edges should work so that the kind of image of that edge is going from the image of its source vertex to the image of its target vertex. So all this boils down to is a very kind of simple and natural notion of transformations between graphs, because what we're really saying here is that an arrow in this category, an arrow from a graph G to a graph G bar, basically just consists of two things. A map alpha 0 from the edges of G to the edges of G bar, a map alpha 1 from the vertices of G to the vertices of G bar, And that's just going to be such that whenever we have an edge, E, that goes from a vertex X to a vertex Y in this graph G, then we're going to have that the image of this edge, so alpha 0 of E, is going to be an edge from the image of X, so alpha 1 of X, to the image of Y, alpha 1 of Y. And that's going to be what these edges in this graph G bar look like. So now we don't have to remember the definition of a graph homomorphism anymore. All we have to remember is that this represents this category of graphs. And that tiny little expression there, if we remember that that represents the functor category, then that tells us what all of these graphs are and what all of the transformations between them are. And moreover, looking at things in this way gives us a much more kind of global viewpoint about what these kind of structured sets are, because of course there can be other structured sets. I mean, what about if we change this category here for something else? Well, we'll see that when we change it for other things, we get other categories. For example, categories of categories where the objects are dynamical systems, categories where the objects are functions. We get all sorts of interesting things by changing this kind of source category here. And we can also go the other way. We could change the category set for something different. So what about if we consider the category of functors from this thing here to a general category C? Well, we can do that, and that will give us some kind of a generalization of the notion of graphs, not graphs which have vertex sets and edge sets, but kind of generalizations of graphs which have some sort of an object representing a vertex set and some sort of an object representing an edge set. So the scope for generalization here is absolutely huge. So now for something quite a lot simpler. We want to understand what dynamical systems are from a kind of categorical viewpoint. And my claim is that they're represented by an expression like this. So I'm going to explain what that means in a bit. So I should say a little disclaimer here. What I'm really talking about is what happens when we have a set and there's a function from that set to itself, and we just keep applying that function over and over again. Okay, so this is close to the definition of a discrete dynamical system. So the thing is that if you look up the definition of a discrete dynamical system, they have kind of this definition, but they also involve the notion of a manifold. So this set has some kind of spatial structure. I'm not going to be considering manifolds, so I'm using the term dynamical system kind of loosely. What I'm really talking about is basically what happens when you just iterate a map from a set to itself. So now let's sort of come back down to earth and look at a really simple example. Okay, so what happens when we have this set here consisting of two elements, 1 and 2, and we do this function on it. So we send 1 to 2 and we send 2 to 1. Well, we could visualize this as a kind of picture like this, where we've drawn these kind of elements and we've drawn the arrows actually inside the set. And this is good because we can think about what happens to an element when we repeatedly apply this function here, and it basically just means we're sort of walking around on this picture here along these arrows. So that's good. Now let's now think about what this looks like in the category of sets. Okay, so this structure here now just becomes a point, this point representing this set X, and we'll have the identity function for that set, and we also have this function f. So this is going to be an arrow from this set to itself. Now what happens when we apply f twice? Well, we just get the identity function. Okay, so if we send 1 to 2 and then 2 to 1, the net result is sending 1 to 1 and similarly sending 2 to 2. So that's just the identity function. So we can really encode what's going on here just by saying that we have this object here and we have this arrow, which if we apply it twice gives the identity arrow. So hopefully you can see that if we just take this object and these arrows, we actually have a category. It's actually an example of a monoid. Okay, so let's have a look at another example of one of these cases where we have a set and we keep doing a function from that set to itself over and over again. And this is going to help us to understand what this little loop means in our expression here. So now let's think about this set of non-negative whole numbers, okay? So 0, 1, 2, 3, and so on. And we'll consider a function from that set to itself, and it's called the successor function, okay? So it just sends a number to 1 plus that number. So 0 to 1, 1 to 2, 2 to 3, and so on. And so we can draw this kind of picture here where the arrows represent how these elements change when we apply this successor function s. And let's also think about what this situation looks like in the category of sets. Okay, so here's our set of non-negative whole numbers, n0, and it has an identity function, id of n0, that just sends every number to itself. And it also has this successor operation. So when we do this successor operation, we're going to send elements to different elements, okay? So what happens when we apply this successor operation twice? Well, that will also be a function from this set to this set, and we could call it s after s. Or perhaps we can write it as s squared, okay? We're thinking of function composition sort of analogous to multiplication, okay? And we could also apply this s 3 times. We could do s after s after s. And that'll be an arrow which looks like this. That's going to correspond to a function which adds 3 to every number, okay? And hopefully you can see that unlike in the last example, no matter how many times we do s, we're never going to get the identity element. If you start adding 1 to a number and you do it over and over again, you never get that number back again, okay? So unlike last time, this kind of system is going to have lots and lots of arrows from n0 to itself. And these arrows are related, okay? So if we apply the successor operation n times, and then we apply the successor operation m times, well, that's just going to be the same thing as if we apply the successor operation m plus n times. Actually, this kind of statement holds in general when you're composing arrows from an object to itself. But in this case, it's kind of interesting because we never get anything but new arrows by composing the old ones with each other. So can we think of this kind of thing with all of these arrows from multiple compositions of s with itself, as well as the identity arrow? Can we think of this as a category? Well, yes, we can, and it's a very important category. So it's sometimes called the additive monoid of natural numbers. Okay, so it has an object, and it has an identity, and it has an identity arrow, and it has some other arrow, s, and then there's an arrow which we could call s squared, which is what you get if you compose s with itself, and then there's s cubed, and all of these different powers of s, and the only thing that we know about composing them is the kind of trivial thing that if we compose s to the power of m and s to the power of n, we get s to the power of m plus n. So if we like, this is a bit of a shift in viewpoint, but another way to think of this is that the identity element acts kind of like 0, and s acts kind of like 1, and composing two of these arrows is kind of like adding. Okay, so 1 plus 1 is 2, 2 plus 1 is 3, and so on. Okay, but more concretely, what this really is it's just a object with an identity arrow and another arrow, and all of the kind of things that we'd get if we keep composing that arrow with itself, and we're assuming that they don't make anything else happen. So unlike the last example, where the function was just switching two numbers around, if you do that twice, you get the identity. There are many other functions which, if you keep applying them over and over again, eventually stuff starts to repeat and there's a kind of closure there, and you can write, well, if you compose this function with itself so many times, it looks like this other function that you get. This is not the case here. Every time we apply the function, it's something different. So all we really have is our arrows. All we can really say about them is this is S, and this is S after S, and this is S after S after S, and so on. So another word for this kind of structure here, when thought of as a category, is it's a free monoid generated by one non-identity morphism, or one non-identity arrow. Okay, that just means we have this arrow that's not an identity, and we just think about what we get using that arrow, but keep things as free as possible. We don't impose any extra conditions, like that when you compose this so many times it is equal to another thing. We don't make any kind of assumptions like that. We simply say that we have all of the arrows from repeatedly iterating. And so this thing here that I'm going to refer to as the additive monoid of natural numbers, that's what this is. Okay, so now we want to understand what the objects are of this thing. Okay, so this little dot with the self loop, this represents this additive monoid of natural numbers. This is not intrinsically defined in terms of the natural numbers. It's just an object with a non-identity arrow which we can iterate indefinitely. It just happened that I introduced it using the natural numbers because it does have this connection. Anyway, we want to consider now what the objects of this thing are. So they're going to be functors from this monoid to the category set. So what's such a functor going to look like? Turns out it's going to look like a dynamical system. Okay, so here's a picture of what one of these functors, one of these objects of this thing will look like. So it's going to send the object here of our additive monoid of natural numbers to some set X. Okay, that's going to be the image of this object under this functor. I'm just calling the object dot, okay, because its name isn't really relevant here. So let's say it sends it to a set. So let's say our functor sends this dot to a set X. And of course, being a functor, it has to send the identity arrow of this object to the identity function of that set. Now, what's it do to this? So what's it do to this non-identity arrow S? Well, it's going to send that to some function from this set X to itself. So an example of this could be this set X could be that set with 1 and 2, and this function could be swapping around 1 and 2. For example, it could be any function from this set to itself. Now, the other thing we know about functors is, of course, that the image of the composition has to be the composition of the images. So we know it's sort of forced upon us that this functor has to send S squared here, S after S, to F squared, has to send S cubed to F cubed, and so on. So we get all of these different arrows which are obtained by repeatedly applying this function F, appearing as these images of these iterations of this arrow S in our category on the left here. So it could be the case that some of these arrows that we get here are equal to each other. For example, the thing I talked about previously had that f after f is equal to the identity, or f squared equals id. And we could have that kind of thing going on here. We don't have to send these distinct arrows on the left to distinct arrows on the right. So hopefully you can see that the image of this kind of structure under this functor is just going to be one of these kind of dynamical systems, one of these kind of iterated maps. And the essential structure of this thing here is just given by knowing what the identity arrow is and what this arrow f is that goes from this object to itself. I mean, yes, we have all of these powers and stuff which are also translated by this functor, but if you're just interested in knowing what's going on, all you have to really bear in mind is that, well, this is a category that has a non-identity arrow, and a functor from this to the category set just sends that object there to a set and that non-identity arrow to some function from that set to itself. So a functor from here to here is just going to basically pick out a set and pick out a function from that set to itself. So let's talk about this category then, this category of functors from the additive monoid of natural numbers to the category set. So now we know what the objects look like, okay? These objects are functors from here to here, but basically they just look like a set with a function from that set to itself, okay? So what are the arrows? Well, the arrows are going to be natural transformations between such functors. So here I've drawn a representation of this kind of monoid here. Now I've just drawn two copies of the object with an arrow between them. That really represents an arrow from the object to itself. I'm calling the object dot. And of course, under this functor f, this is going to change to a set x with this arrow little f from that set to itself. And so this is one, and so this is really one of our kind of objects in this category. And then here's another one corresponding to this functor g. This is sending dots to this set y, and it's sending s to this function g from y to y. So okay, all we have to ask ourselves now is, what's a natural transformation from this functor to this functor? So let's say we have a natural transformation alpha. What's that going to look like? Well, it's just going to have one component, which we could call alpha dot, which goes from where dot gets sent to under f to where dot gets sent to under g. So it just has one component, alpha dot. And there it is again. And then, of course, this being a natural transformation, we require this square to commute. So basically what that means is that we require g after alpha dot to equal alpha dot after f. Okay, and so this is our natural notion of arrows between these kind of dynamical systems. Okay, so alpha dot's just going to be a function from x to y which satisfies this property. Okay, so in the category of sets, the objects were sets, and any function from one set to another was considered an arrow. In this category of sort of dynamical systems, the objects are sets with these functions to themselves, and you know, this one's equipped with a function little f, and this one's equipped with a function little g. And if there's an arrow between these dynamical systems, that's just a mapping of sets, but it's a mapping of sets which respects structure in the sense that this equation holds. You may be thinking, well, how do I know that this thing's natural when I consider iterated functions? So what about if I applied this function n times, and then this would be f to the n, and this would be little g to the n. Okay, well, it turns out that such a square will also commute as long as you have this condition. Okay, so okay, now we can succinctly summarize like what this thing looks like, and basically we can say that it has objects which consist of a set and a function from that set to itself. So I call those dynamical systems, and we'll have an arrow from one dynamical system to another. What will that be? Well, it'll just be a function from the set x to the set y, which satisfies this condition here that g after alpha equals alpha after g. Okay, so this is fun. So let's do one more. What about this one? What's this represent? Well, it's going to be a category, and the objects are going to be arrows from set. In other words, the objects are going to be functions. So just using this same kind of device, we can make lots of interesting categories. And this one actually has objects which represent arrows from this category set. So how does this work? Well, you see this little picture at the top right, that's just two dots and an arrow. So that corresponds to this category here, where we have two objects and an arrow between them. We have identity arrows too, but I'm not drawing those, okay? And what this notation says is that the objects in this category are functors from this little two object category here to the category set. So what are these objects going to look like? Well, they're going to send this object 0 to some set x, and this object 1 to some set y, and then this arrow q from 0 to 1 is going to get sent to this arrow f from x to y. So that's just going to be a function from x to y. Well, okay then, so what about so basically our objects are nothing more than functions in this case. This function f, together with the information about what its source set is and what its target set is. Okay, so what about the arrows then? What are the arrows in this category? Well, the arrows, this being a functor category, are going to be natural transformations between these functors. So let's suppose we have another functor. It sends 0 to x bar. So this is f bar of 0. And let's say now it sends q to something we'll call little f bar. And let's say it sends this object 1 here to something we'll call y bar. So to find out what an arrow is, all we have to do is understand what a natural transformation alpha from f to f bar is going to look like in this picture. And what is it going to look like? Well, the 0th component is going to go from x to x bar. There's alpha 0, very good at chess. And here's alpha 1. So alpha 1 is going from where 1 got sent to under f to where 1 got sent to under f bar. And this being a natural transformation, we of course require that this square commutes. Okay, so now we can just write down a description of this category here. Okay, so this category has objects as functions like this. So a function from a function f from a set x to a set y. And what are the arrows? Well, they're these natural transformations, but if we want to say it in more kind of explicit terms, we could say, well, an arrow from f to f bar is basically a pair. Alpha 0 sends the source of f to the source of f bar. Alpha 1 sends the target of f to the target of f bar. And we have to have this kind of square to be natural. So we have to have that f bar after alpha 0 is alpha 1 after f. And that's it. And also we can generalize this. So we can consider the so-called arrow category. So if we have a general category C, we can make this kind of arrow category, which is just the same idea, has just the same kind of definition here, except where I've said function there, we just say these are going to be arrows of the category C. And, you know, we still want this naturality condition to hold. So it's basically a very similar kind of setup. Okay, so we have all these different categories. Now, I've basically today just been trying to show you how to define these things in an elegant way, and I urge you to investigate these categories yourself. For example, what are the terminal objects if there are any? What are the initial objects if there are any? What's the notion of product if there is one? And all of these questions are great questions, and basically just familiarizing yourself with the different kind of objects in these categories and what the arrows look like. For example, sitting down and doing a few examples with dynamical systems and trying to get a feel for when there's going to be an arrow from one dynamical system to another and what the different arrows are like. That's a wonderful exercise, which I urge you to do. But I'm basically just trying to show you the kind of high level stuff. So this next thing is about subcategories, and it's very interesting, but it's not something I'm going to build upon a lot in this series of videos. Anyhow, let me explain, because it's a really great kind of exercise in thinking, and it gives us a kind of higher level appreciation for how these structures are interrelated. So the basic thing that I want to get across is that of these three different kinds of structures, dynamical systems, functions and graphs, the graphs are the most complicated ones. And in fact, you can represent systems of the first two kinds, the dynamical systems and the functions, you can represent those as graphs. Okay, so we can say this more precisely with some statements about subcategories. So the first statement is that this category here of functions is isomorphic to a subcategory of this category of graphs. So firstly, let me tell you what a subcategory is. So if you have some category, then a subcategory of it is a category which you can obtain by taking that original category and then possibly removing some of the objects and some of the arrows. And I'm saying that this category of functions here is isomorphic to a subcategory of this category of graphs. Now, some mathematicians would probably just say that this is a subcategory of this. But I want to be a bit more precise. So if we're being really precise, we'd probably say that the objects of this category are functors from this category with one non-identity arrow to this category set, whereas the objects of this category are functors from this category with two non-identity arrows to this category set. So if we're taking that kind of view, perhaps we'd say that the objects of this category are fundamentally different to the objects of this category. And so perhaps it would be wrong to simply say that this is a subcategory of this. But it it looks the same, okay? It looks the same as a subcategory of this. So what I'm saying is that if we draw this category of graphs, so we have these different, this is just an illustration, but we have these different objects here representing graphs, and these different arrows here representing graph homomorphisms, then I'm saying that we can find a subcategory of this. We can get rid of some of the objects and things, and we end up with this subcategory U. And that subcategory U basically looks just the same as this category of functions. In other words, it's isomorphic to it. So two categories are isomorphic basically when they look the same. Many category theorists would just say they are the same in such a case, when you can sort of just relabel the objects and arrows in one category to make it look identical to the one and the other, to make it look identical to the other category. More precisely, two categories are isomorphic when there's a functor from the first to the second, which puts the objects and the arrows in one-to-one correspondence with each other. Okay, so what's the intuition behind this result? Well, the basic idea is that you can represent any function by a graph. Okay, so here's a function f which goes from set x to set y, and we can sort of think of this as an object of this category of functions, because we have a functor from this two object category, a functor f, which kind of defines this substructure of set. This functor sends this object 0 to this set x, this object 1 to set y, and this arrow q to this function f. So the question is, can we also represent this kind of thing in the category of sets using graphs? Or in functor speak, can we find a functor from this category here, which we're using to make our category of graphs, which gives us this? Well, yes, we can. It's quite easy. We'll just send 0 to x, 1 to y, and we'll send both of these arrows here to the same thing. We'll send both of them to f. Okay? So let me just go through the kind of simplest view of this category and this category so I can make this kind of relationship more transparent. So this category of functions here corresponds to the category which has objects as functions, and the arrows are going to be pairs of maps. Okay, these are really natural transformations, but we'll not talk about natural transformations at the moment. Let's just take a kind of more down-to-earth view of what these things are. So an arrow from this function f to this function f bar consists of these two maps, alpha 0, which sends x to x bar, and alpha 1, which sends y to y bar. And crucially, these have to be such that this diagram commutes. Okay, so alpha 1 after f is f bar after alpha 0. So that's our definition of an arrow from one function to another. When I say this category here corresponds to this, I'm really meaning it's isomorphic to this. Okay, so I'm saying the category of functions is isomorphic to this category. You see, you could, if you're being really kind of picky, you could say, well, actually the objects of this category are functors from this category to this category. And, you know, if you want to set things up like that, you almost see this kind of form for the category, but, you know, technically you could say, well, these are actually functors from this category, and there's identity arrows involved, and so on and so forth. But the point is really we can forget about all those details, and we can just think of the objects here as actual functions. Now, the category of graph, similarly, it corresponds or is isomorphic to the category which has objects as these pairs of functions, s and t, from an edge set to a vertex set. And then the arrows have a very similar definition. So an arrow from one graph to another graph, this one has E and V, and this one has edge sets E bar and V bar. And an arrow alpha from the first to the second is a pair of maps, a pair of functions. Alpha 0 sending the edge set of the first to the edge set of the second, and alpha 1 sending the vertex set of the first to the vertex set of the second. And these functions here, alpha 0 and alpha 1, have to be such that they make two different squares commute, one for the s's and one for the t's. So we have to have that alpha 1 after s is s bar after alpha 0, and alpha 1 after t is t bar after alpha 0. That's our definition of an arrow from one graph to another, basically a graph homomorphism. Okay, so what's going to be the subcategory U of this category of graphs, which is isomorphic to this category of functions here? So basically this subcategory U of our category of graphs is just going to be the subcategory of this which has all the objects which have the source function equal to the target function. Okay, so when the source and the target functions from e to v are the same, we essentially just have one function from e to v, or if you like, two copies of the same function. And that looks just like this, where we just have one function from x to y. So these objects clearly look the same as these objects in our category of functions here. And so if we just take those objects as a kind of subcategory of the category of graphs, and then all of the arrows between them, so all the arrows between such objects in the category of graphs remain in this subcategory U, then that's clearly going to look the same as this category of functions. Okay, and it's basically just this idea that if we consider a graph where the source arrow and the target arrow are kind of collapsed on top of each other, that's essentially just two sets with a function from the first to the second, and we can emulate arbitrary functions from one set to another in such a way. Okay, so this result here, that the category of functions is isomorphic to a subcategory of the category of graphs, actually relies on a kind of interesting way of representing a function using a graph. And this is an idea called a bouquet. So, I mean, let's say we have a function f from a set x to a set y. Well, I've basically said that we can find a graph that corresponds to that. So if we have a graph like this with an edge set v, with an edge set e and a vertex set v, and a source function s and a target function t, well, you know, we're going to have s equal to t because we are considering these special kind of graphs which correspond to functions. And then how can we find such a thing which looks like this function? Well, we'll just set e equal to x and v equal to y, and this source and target both equal to f. Well, let's think about what that actually means as a graph. So that will be a graph which has as its vertex set this target set y here. So these are going to be the vertices a, b and c. And the edge set of this graph is going to be corresponding to this set x. So we're labeling our edges of the graph with members of this set x. And we're also going to have that the source of an edge is equal to its target, and that's equal to the value of f that we get when we apply this function to that corresponding element. So we can visualize that 1 is sent under f to a by drawing this directed edge 1 here, which starts at a and ends at a. We can visualize that 2 is sent to b by saying that there's an edge labelled with a 2 which starts at a b and ends at a b. And similarly 3 is mapped to b, looks like this. So this is the idea of a bouquet, and so each of these gets get some kind of flowers representing how these functions work. Okay, so the next result is really cool. We're going to show that the category of dynamical systems is isomorphic to a subcategory of the category of graphs. Now, the reason that this is so cool is because one of these dynamical systems, basically, we can think of it as a function from a set to itself. Now, if you have a function from a set to itself, there's a way that you can draw that as a graph. You basically have a dot for every element, and you draw arrows to show how those elements transition when you apply the function. And that's a graph. And so what we basically are going to see from this kind of demonstration is the kind of deep reason why that kind of thing can be done. Okay, we know we can do this. If you've played around a bit with functions that map sets themselves, you'll know that we have this kind of representation, and we kind of understand it pictorially, but we're going to understand it at a kind of deeper level by thinking about these subcategories. So if we have a dynamical system, officially it's a functor from this additive monoid of natural numbers to this category. So it sends the object of this monoid to a set X, it sends the identity arrow of it to the identity arrow of X, it sends this non-identity arrow S to some function F from this set to itself, and it will also send S after S to F after F, S after S after S to F after F after F, and so on. But we don't need to worry about that now. So the question is, can we represent this sort of thing as a functor from this two object category here involved in the category of graphs to the category set? And yes, we can. So here's a way to do it. Let's send both of these objects here to this set X under our functor, and we'll send this arrow B, we'll send that to F, and we'll send this arrow A to the identity arrow. So that's a way that we can essentially obtain this sort of structure in the category of sets by using a functor from here to here. And this is the sort of essence of this idea. Let's go through it in more detail. So I've already talked about how the category of graphs corresponds to these kind of objects with these kind of arrows, which are essentially maps of edges and maps of vertices with these two squares having to commute. What about this set of dynamical systems? Now, officially, it's this category of functors from this monoid here to the category set, but an isomorphic kind of category, which is much easier to think about, is just this one which has objects as functions from a set to itself. Okay, so what about the arrows of this category? Well, if we have a couple of objects like this, so we have a set X with a map F to itself and a set X bar with a map F bar to itself, then an arrow alpha from this object to this object is just going to be a function which sends X to X bar, which makes this square commute. Okay, so we want alpha after F equals F bar after alpha. In other words, if we apply this function in our dynamical system and then we do this mapping to another dynamical system, that should give the same results as if we first do the mapping to the other dynamical system and then we do the function over there. Okay, that's the essence of what this kind of arrow from one dynamical system to another does. So, okay, what's my claim then? My claim is that there is a subcategory of this category of graphs, subcategory V, which is isomorphic to this category of dynamical systems. Okay, so what is this subcategory V then? This subcategory of the category of graphs, which is isomorphic. to the category of dynamical systems? Well, it's just going to have objects like this, these graphs. So we have an edge set and a vertex set and a source arrow and a target arrow, but we're restricting these. We're only selecting certain objects from this category of graphs, and those are the ones which have the edge set equal to the vertex set and this source arrow just equal to the identity arrow of such sets. And so we consider these kind of restricted graphs, and they're going to be the objects in this subcategory V. And what are the arrows in this subcategory V? Well, they're just going to be all the arrows which were present between such objects in the category of graphs. So let me explain the kind of visual intuition behind this. So here is a dynamical system. We have a set X and this function f back to itself. So we send 1 to 2 and 2 to 1 and 3 to 2. And we can of course visualize this with a picture like this. So we just draw all the elements of the dynamical system, 1, 2 and 3. And then we have these arrows here, which represent how those elements transition when we apply this function. It's a great way to represent these kind of dynamical systems like this, because then iterating the system is just walking around on such a graph. Yes, this is a graph. And this is the thing. You see, if we label, so this graph has a vertex set, which is equal to X. And notice that I'm also labeling the edges of this graph with elements from X. So the edge set and the vertex set, okay, I haven't drawn them in the same way, but I've labeled them in the same way. We can think of them as the same in a sense. They're the same, it's two copies of the same set. It's just the green things are drawn with arrows and the red ones are drawn with dots. So we think of this edge coming out of 1 here. We also label that with 1. And this is an edge which has its source vertex equal to the vertex with the same name. So its source is also 1. And where's its target? Well, the target is going to be f of 1. It's where 1 gets sent to under our function. And similarly, we have this arrow here. So this is identified with this element here, and its source is the same as this vertex here. And the target of this arrow is f of 3, which is 2. Okay, so this representation of dynamical systems using graphs is exactly what this type of correspondence piggybacks on. And okay, so maybe you buy this, that, you know, we can represent these kind of dynamical systems like this, with graphs like this, with these kind of restrictions. So you see how we can represent the objects, but what about the arrows? I mean, there are arrows of this kind, which are basically one function from x to x bar, which require this square to commute. But the arrows in the category of graphs look more complicated, right? We have two functions, alpha 0 sending the edge set of one graph to the edge set of another, and alpha 1 sending the vertex set of one graph to the vertex set of another. And we have these two different commuting squares. So how can we see that the arrows in this category V, so there are going to be arrows defined like this, but restricted to objects like this, how can we see that those kind of arrows look like these kind of arrows here between dynamical systems? So, okay, what we're basically doing then is we're looking at these two pictures, and we want to somehow see that under these restrictions, they boil down to a picture like this. So the first thing is that we've got E equal to V. So the corners of our squares are just going to involve, you know, the same sets at the top and these other sets at the bottom, but they're going to be the same as each other on the left and right, okay? Similarly here. But still, we have these two different commuting squares. But let's think about this one, okay? Notice that we're setting S as equal to the identity function. So if you think about what that means we're going to have ID after alpha 0 equals alpha 1 after ID. And that implies that alpha 0 equals alpha 1. And that's great because that means that this is just going to be two copies of the same map. And this kind of commuting condition just evaporates. It's obviously true. I mean, it forces alpha 0 equals alpha 1, and when alpha 0 equals alpha 1, it's obviously true. So that evaporates. And then we've just got this one commuting condition, which looks just like that. So these arrows here, when we're restricting ourselves to these kind of objects, the arrows between them are just two repeated copies of the same kind of alpha map, which just makes one square commute with the t's. And so if we do these kind of substitutions, x is equal to e and v, and t is equal to f, then these two commuting squares are just identical. So we see that indeed arrows in here, and so we see indeed that arrows between a pair of objects in this category V look just like arrows in our dynamical system. Okay, so finally, to complete this picture, I want to convince you that the category of dynamical systems is isomorphic to a subcategory of the category of functions. So I'm claiming that we can find a subcategory of this which is isomorphic to this category of dynamical systems. Now, this is sort of intuitive because we can basically think of this as having objects which are functions from a set to itself, and this just has objects which are functions. So, you know, functions from a set to themselves are a special case of functions, right? And that's the basic idea behind this sort of correspondence. So we find the subcategory W of the category of functions, and to do that we just select all the objects of this category which have x equal to y, and they're going to be all the objects of this category W, which is isomorphic to this category of dynamical systems. But there is a bit of a subtlety here. You see, in this case the arrows are pairs of maps, alpha 0 from x to x bar and alpha 1 from y to y bar. Well, if we just set x equal to y, then our arrows are still going to be different to the arrows over here, because these arrows between the dynamical systems, they're just consisting of a single map from x to x bar. But these arrows are sort of more free because we can have two different maps, an alpha 0 from x to x bar, and when we impose x equal to y, then it'll be an alpha 1 from x to x bar. So there'll be two kind of functions that we could choose over here, and those would just have to be such that these kind of square commute. So if we just stopped here and we just said, oh well, let's just select these objects and have all the arrows between them, then we'd have too many arrows, because we'd have arrows which have alpha 0 and alpha 1 different perhaps. So we have to also restrict our attention to certain arrows. So what I'm saying is that to get something that looks like this category, we're taking our category of functions, we are just looking at the arrows between a certain subset of those objects, these ones which have x equal to y, but we're not taking all of the arrows between those objects. We're only taking the arrows which have alpha 0 to equal to alpha 1, and then this will look just like this, and we're done.